Welcome guys. So in this video, what we're trying to do is quickly introduce the Bloch sphere. Okay, so the first statement, what we gonna say is that how to map the pure state to Bloch sphere. Okay, so the map is very easy because we know that the single qubit can be written as the combination of 0 and 1. And there's a phase, right? There's a ultimate phase. So I can set up the first one. Let's say this is A, alpha, and beta. I can set up alpha to be real, and beta. I can force alpha to be real. So I can let alpha to be just cosine theta divided by 2, and this one to be sine theta divided by 2, right? But there is a complex vector. Factor should be here, right? Because otherwise everything will be real. So the beta I define here. So now single qubit state defined as theta and phi. So I can just plot theta and phi into a three-dimensional vector like theta and phi. So the standard spherical coordinates. So that means the single qubit state mapped to the vector. So this is the single state, single vector. Okay, let's say it's three-dimensional. Okay, that's it. Okay. Now the second question, what people like to, what we like to ask is how to map to how to map a mixed state. Okay, so the starting point is that the mixed state rho is a 2x2 matrices, right? If we just generalize the qubit states and satisfy the rho equals to the rho should be Hermitian, and the trace of rho is 1. So notice that the rho, the definition for rho is here in the general case like P111. So I should say the mixed state means that the P rho can be written as some also gonna tell state phi1 phi1 plus P2, right? Phi2 phi1. So it's the ensemble. So basically P1 plus P2 is 1, and the P1 okay. And the P1 and P2 are just can be interpreted as a probability. So P1 is less than, larger than 1, larger than 0, larger than 0, larger than 0. Okay, so and combine these two properties, all the states we can write this rho is half 1. This is identity matrix 2x2 plus a sigma. Okay, so if I take a row of this, I will get 1. So the reason is that the Pauli matrix are traceless. Right, so this tells you that the trace of a dot with sigma is 0. So if I take trace, then I get 0. So I get the half times 2. Okay, so the map. So I map the density matrix identity plus a times sigma to the a. So this is the Bloch sphere map. So basically, this is like the generalization of the what we in the pure state. So in the pure state, we just write a 0 and 1 to this form and then map it to a. But in this way, I do exactly the same thing, but the only difference is I map this a, right? I change the mixed states and map this a as the mixed states. Okay, so the third property is that I want to prove probably the most important theorem in the Bloch sphere. Okay, so theorem is that so there's a mixed state, right? So suppose somebody gives you a state and then you don't know whether it's mixed or not, right? So basically you will map it into A. Okay, so theorem means that the result is if A, the norm of A is 1, the norm of A is 1 if and only if a rho is pure. So that means if A is not 1, and we will show that you only less than 1, then if only if rho is mixed. Okay, so this is the theorem I will prove. Okay, the proof is very simple. The reason is that we know that the trace row, right, is just p1 plus p2. So the trace row square will be p1 squared plus p2 squared. So it should be less than p1 plus p2 equals to 1. Right? The equality only holds for p1 is 1 or p2 is 1. So that means if row is pure, if only if trace row square is 1. Okay, so let's prove. Let's see what is the trace row square for these matrices. Okay, so suppose we square and 1 over 4 identity plus a sigma I plus a sigma. So it's very quick. 1 over 4 identity to a sigma square. Okay, take row square. So the first term is a 2 by 2 matrices, you get 2. The second term you get 0, and the third term you will get here. Okay. So what is the a sigma square? Okay, so this is just by definition ai sigma I, aj sigma j, aj, and now I can write the sigma I sigma j as the anti-commutator because ai ij are symmetric, and I need to put a half. So this is aj ij ai aj, and then this is 2 delta ij. So this is delta ij. So this is summation ai square. Square thinks that the j can be need to be same as I. So this is the norm of the a square. So the vector norm and 2 by 2 matrices. Okay, so let's delete this standard derivation. So we get 1 over 4, 2 plus 2 a norm square. So it's a half 1 plus a square. Okay. So we get what, right? So we have this. Okay, so we already know that trace row square equals to 1 if only row is pure. Right, so if you change it to this, you will find that only if a is 1, right, this is 1, so row is pure. Right, if row, but usually if row is mixed, then trace row square will less than 1. Then corresponding to a square is less than 1. Row is mixed. So combine all these two. Okay, so this means that if a state live on the unit sphere, a state is mixed. Sorry, state is pure. Otherwise means that states live inside. So a is less than 1, right? The magnitude of a vector is less than 1. So the states live inside a unit sphere. So the state is pure. State is mixed. Sorry about that. I always say converse results. Okay. So probably this is the most important theorem for the box sphere. I should say probably the only theorem. Okay. And I will see you guys in the next videos. Be sure to subscribe to my subscribe to my channel. Thanks.